today is going to be this idea, the idea of a transfer function. Okay, so I'm going to try different pens today and see if everything shows up well. All right, you recall the last time we met, I said that from an abstract standpoint, a very simple model of a control system might be something that we draw, like this. And today I hope to receive from most of you a biography, a short biography describing who you are and your interests and what your dreams are. And then at the end of that biography, maybe something that interests you in life, described in the context of a control system. And we said that a very simple control system, this would be the process or the plant, and this might be the controller. And these arrows represent information or signals. And so this would be the simplest block diagram. So today, the idea we want to talk about is, this is abstract, how do we make it a little bit more concrete? And we want to ask the question is, what is the math that goes on here? What is the math? What is the model or the math that goes in here and here, like so? And so what we're going to do is we're going to reach way back in our academic history, and we're going to go back to linear systems and signals, and we're going to kind of recall from here, the course is 2120, I think, is linear systems. And so there was this idea of what we call the Laplace transform. Okay? And the key idea with the Laplace transform is that we could take a piece of information, a signal, let's call it y of t. This here is time. And we do some hairy mathematics called the Laplace transform, which you exercised here. And then what we do is we get the same information but expressed in a different language called the Laplace transform domain, the transform domain. And to distinguish between the time domain and the transform domain, we use different notation. So what I want to first of all say to you is this is some information y. This is the same information y, okay? But this is in time. This is in what we call the S domain or the transform domain. This is like speaking at home in English, but now we decided to take a trip over to France. And yeah, we could use English over in Paris. We'll get along okay, but we have discovered that if we use French to say some words, the locals will treat us more nicely. Okay, so that's basically it. It's the same thing. This is something of interest. This is the same thing of interest. So this is bread, but this is in English and this is in French. So the Laplace transform is just translating something into another domain where life could be easier, or life might be easier. And for us, the Laplace transform is going to make our life a little bit easier because the math is going to be a little bit easier. So this is what we call the transform domain. It's a transform variable. Okay. And my analogy of English and French is not the best, but it kind of helps a little bit. Because when you get over to France, you could kind of mix your English and French together. You absolutely have to, and the French will probably snicker at us. But really, we should, when we're in France, we speak French, and then when we need to get back home, we speak English. All right. Now, the important thing that we want to carry away from us from 2120 is not that Laplace transform integral and that inverse Laplace transform integral. We'll never have to do that again in life, probably. Okay, I can say certainly in my 60 years of life, I've never had to do that after I left school. So we can all cheer and say yay. Okay, but what I did have had to do is kind of remember some simple, basic transform pairs and some key concepts. And one of the key concepts is that if I take some idea and transform it and call it capital Y, and I'm looking at a dynamic system, then I'm interested in looking the dynamics of this thing. So I might be interested in a signal what we call dy dt. Okay, this is maybe position. This would be speed. Okay, so change in position is going to be speed. So I'm interested in also dy dt. Dynamic systems can be described by differential equations, which is why we study differential equations. And this is why we have these expressions dy of dt showing up. We might use this notation, y dot, the dot meaning dy dt. The main thing that we want to take away for this class from the previous class is that if I decide to take an idea and transform it and call it capital Y, then its derivative transforms this way. Okay. You might remember this equation. Let me pick this equation apart a little bit. This d by dt is what kind of math? Calculus, right? We see the dot and we remember, oh, calculus. Now I remember why, well, now I understand a little bit better why they put Cal 1, Cal 2, diffie-Qs in my curriculum model. Now I know why those professors said I had to take it. Because I want to study dynamic systems, and so dynamic systems are described by differential equations or can be described by differential equations. So that's why this is calculus. And do you remember how do we solve differential equations? There's a lot of methods we learned, right? Method of unknown coefficients, separation of variables, blah, 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 blah. It probably wasn't a lot of fun. Okay. Over here, we take the same idea, but what we're saying is that the differentiation in time is equivalent to taking the information and then doing this to it. How would we describe this operation? What have I done to this when I write this out in front of it? What mathematical operation is this? It's multiplying by s, right? I just take whatever information I have and I multiply by s. Here I say I have a piece of information and I put this operator, this symbol d by dt. Well, the symbol d by dt means differentiation. That's a calculus operation. But here, when we go to the other world, we say, hey, if this is a piece of information and this is its derivative, I represent that just by simply multiplying by s. Okay? So think about d by dt in time suddenly becoming just multiplying by s. Now, multiply is what kind of math? Algebra. Now, that should please us because generally we think algebra is easier than calculus. So this is why we use the transform. Because instead of having to remember all our calculus, we can say, let's use algebra to solve things. Because when did we start learning algebra? What grade?
First.
Liar. For me, Algebra 1 was 9th grade. But I grew up in the hills of East Tennessee, so I think some of you more advanced people probably took algebra 7th grade, something like that. So it's a concept that we can recall. It's much easier. You know, you don't have to wait till you're in college to learn this math. You learn algebra at a much earlier age. Of course, now the difficulty is because we learned algebra back in 7th grade, and now we're about 10 years further along, we maybe have forgotten some algebra skills. So that's where we might get tripped up. And so this is where in this class, if you're thinking, man, I understand the concepts, but I'm getting tripped up, most of the time it's because we're making algebra errors. Okay, so the takeaway is d by dt, this operator becomes this. Instead of a calculus operator, we just simply multiply by s. Now this thing here, this is the completion of the rest of the equation. It says that the differentiation, I have to just do this algebra, but then I got to subtract out this idea of a initial condition. This is the initial condition. The initial condition. So let me just clean up this. This is getting a little bit messy on this page. I'm just going to just take away and just say on one page the key idea we want to carry forward with us. Okay, this is calculus. This is calculus. This is an algebra. differential algebra. It's a multiply. Okay, let me do another calculus. What is this? Do we recognize this symbol? If I squiggly something, dt, what am I doing to that thing? I'm integrating. That's the other calculus thing we learned, right? And we kind of remember that integration is kind of the opposite of differentiation, right? If I differentiate something and I want to undo it, I got to integrate it. Or if I integrate something and I want to undo it, I got to differentiate it. So they're kind of like the opposite of each other, right? What is the opposite of multiplying by s in algebra? Dividing by s. Okay, so all of a sudden, rather than doing a calculus operation, what I need to do is I need to do a divide. Okay? So this is the concept we carry away with us when we want to derive transfer functions. So let me go back again and talk a little bit some more about something we took out of 2120, and that is the transfer function. So I have a system here. I have an input, and this is the output. And we ask, what is the transfer function? Well, the transfer function is the ratio of the output over the input in the transform domain. So let me give this output, its time domain expression might be y of t. Its transform is y of s. Over here, the input, maybe we call it x of t. Its transform, we're going to call it capital X of s. Okay? And you say, wait, what's the difference between capital and lowercase? It's just a way to help us remember that one's in time domain and one's in transform domain. So the transfer function, we have to remember, is the ratio of output over input. So it's y of s over x of s. This is the transfer function. This is the thing that we put in the box here. Okay, y of s over x of s. Okay, so it's a ratio, output over input. That's this idea. Now, a very common thing to do while we're still learning, getting used to this idea of Laplace transforms and stuff like that is sometimes we get the idea, well, it's just a ratio of output over input. And so we're tempted to say it's y of t over x of t. Okay, we're tempted to write this. But this is not a transfer function. Okay? This is a ratio. It is a ratio of output over input, but it's a ratio in time. And the transfer function is not a time domain concept. So we need to say, don't do this. Okay? It is not a ratio in time. It is a ratio in the transform domain, the S domain. We also call it the frequency domain. Those are all synonymous words. All right? Let's derive a few transfer functions. Do a few examples now. Okay? So let's, as a first example, let's suppose that we're doing a circuit analysis. Here's our system. I'm going to draw a circuit here. It's got an inductor, and it's got a resistor, like so. And here's a current. Move it a little bit. There. Okay. Sorry about that. Okay. We have this circuit. It's just a RL circuit. It's got a voltage input, and maybe we're interested in I as the output. So let's suppose that I is the output, Vn is the input, and I want the transfer function for this that describes this problem. Okay, I wanted the transfer function that describes this problem. What I could do is, since this is a loop, I see this, I'm going to use the signs, all the signs that I can bring into the problem. Okay, so that's one modeling approach, is use all the signs that we can bring into the problem. This is an analytical modeling approach. And so we think, what science could we maybe apply to analyzing this? What in our engineering or our education can we apply? Suggestions? Come on, we got 50 people in here. Sure, we got some ideas.
Kirchhoff's.
Circuit analysis. Okay, let's try circuit analysis. Let's try circuit analysis. We'll do Kirchhoff's voltage law. Okay, what is Kirchhoff's voltage law? Kirchhoff's voltage law basically says that sum of voltages in a loop is equal to 0. Okay, so if I were to sum all the voltages around in the loop, I would get it equal to 0. We may recall that one of the things we could do is we could redraw this circuit, and I'm going to redraw it and use some S-domain notation, Laplace transform notation. So I'm going to just redraw this, and rather than calling this Vn of t, I'm going to transform. I'm going to call capital Vn of s. And then I have this current here. Rather than calling it I of t, I'm going to call it capital I of s. And this inductor here, I'm going to stick in, since we're dealing with Kirchhoff's voltage law, we'll deal with impedances. Let's review our science, our circuit analysis. What is the impedance of an inductor? SL. Okay. And then we need to do the same thing with R. We're going to replace R by its impedance, which is R. Okay. So then what we can do now is we can write Kirchhoff's voltage law. Sum of voltages around the loop is equal to 0. But we'll use this notation here, and we'll get something like this. We'll say that Vn, capital Vn of S is equal to, let's say we got a drop, this drop is equal to all the drops around the loop, or this rise on this side is equal to the drops on the other side. And so I got a drop here, and so that'll be I of S times SL plus the drop across this, which is I of S times R. Okay. And so notice that this is an equation that's just an algebraic equation. It involves functions of S, but it's just algebra. And we see these functions are scaled by constants S and operators SL. Now we can do algebra. We don't do calculus anymore, we do algebra. And so we clean up our algebra a little bit. We can factor out the I of S, and then we have SL plus R. And then what we want to do is we say we want the transfer function, which is a relationship between the output over the input. So we need to do a little bit of algebra, and we want to write I of S over Vn of S. We do a little bit of algebra there, and we get 1 over SL plus R. So this is our answer. This is my transfer function for this circuit. I'm going to pause there for a moment and ask if there are any questions. Okay. Now, there's more than one way to skin a cat. We could have gotten there not necessarily by doing this. We could have written differential equations to describe this. We could say, oh, what is the voltage drop across an inductor? V is equal to L d I dt, right? V equals L d I dt. Voltage drop across the resistor is R times I. We'll probably use the lowercase notations for the I because we're writing them in time domain. And then we could then transform that differential equation. I'll do an example of that hopefully before we leave. Okay? Notice this transfer function. This is the model now. This is the model that we put in the box that says we would draw a symbol like this. We say the transfer function for this system is a box now. The model is SL plus R. The output is I of S, and the input is Vn of S. So this is the transfer function concept, and this is the model that we will put in. Okay. So what's behind this box? It's that circuit. It has a resistor and an inductor. That's a bunch of symbols. We could have described that circuit with differential equations, other equations, but this is just a language that we, as electrical engineers, understand. Okay. All right, let's do maybe another example. Let's do maybe we have a model. Maybe we have a model where y is the output and u is the input. Okay? And it's described by an ordinary differential equation. Linear ordinary diff-EQ model. And the model might be, now I'm just going to dream one up out of my head. I'm going to say maybe it's y triple dot plus 4y double dot plus 3y dot plus 2y is equal to 6u dot plus 5u, something like this. Okay? This is a calculus expression. This represents the input signal. This represents the rate of the input signal. This is the output, its derivative, its second derivative, and its third derivative. Okay. So what we would do is, to find the transfer function between output and input, we're going to transform this thing. We're going to do the Laplace transform. Okay. And so y becomes y of s. The 2 carries long, it's just a scaling. Okay. And then here, y dot becomes what? We're going to maybe go back and we say dy dt becomes this whole big expression. Okay. So we have s y of s minus y at time 0. I'm going to put a bracket around it and then put in a 3. Okay. I'm not going to have room to put all this equation in, but I'm just trying to illustrate what we're doing. We're simply just translating English to French. We're using a new notation. Instead of lowercase y of t, it becomes capital Y of s. Scale it, and we'll do this. Okay, at this point, you could probably go through and do all the rest. Same sort of idea. We'll do that in a moment. But before we do that, I want to talk a little bit about this animal right here. Okay. Now, the transfer function, as I said earlier, the transfer function is a concept that describes, what does it describe? It describes the relationship between, here, let me go back a slide. What does the transfer function describe? The relationship between these two variables. Okay? Systems are dynamic, okay? I'm going to buy a car. Okay, let's talk about a car for a moment. I want to know how this car performs, its dynamic behavior. Okay? So, how fast is the car going to roll on the road? It depends on the inputs, right? So what are the inputs in driving a car?
Pressing the pedal.
Pressing the pedal, okay? What else can affect the speed of a car?
The weather.
Weather, okay, good. How about if I park the car on a hill, right? Then even without input, it can roll, right? We call that initial conditions. Okay. So when you go out and test a car, of course, what you're going to do is you're going to jump in the car at the dealership and you're going to drive it and you're going to press the pedal and stuff like that. And whether you go up the hill or down the hill, you're going to try to kind of remove that out of your mind. You jump in the car and you press the pedal and it doesn't accelerate real fast, but you tell yourself, oh, it's okay, we're driving uphill. Okay. Or you jump in the car, you press on the gas, and it goes zoom. And you're saying, well, it feels like it's going really fast, but wait a minute. I'm going downhill. So you try to take all that out of your mind because you really want to know how the car is going to respond to the throttle. So you drive around town, uphill, downhill, flat ground, all that sort of stuff, and you just kind of try to take out of your mind the effects of the environment, the weather, the initial condition, you take those out. Because those are not inputs to the car. They affect the car performance, but they're not an input. Okay? So, let's go back to our differential equation problem. I want to find the transfer function between input and output. Is this related to input-output? No, it's the environment. It's the initial condition. So I need to remove it. So for the purposes of this class, we're going to ignore this. Ignore initial conditions in transfer function development. Okay? If somebody says, I need a model of the car, they're talking about, I want to know how the car responds to input, to steering, to throttle, and so forth. Okay? They want to say, what's the 0 to 60 time for this vehicle? And we wouldn't say, well, let's put it on the hill and get our numbers down so that it rolls faster, right? No, they don't want that. We got to ignore it. Okay? So they want the transfer function, the model, we ignore it. Now, if they ask a different question, suppose they said, what's the response of the vehicle over time? Okay? What's the vehicle response over time? Then you're going to say, well, a lot of things can affect the response. The throttle and the initial conditions. In that case, we better have this in here. Okay. But if the question is, what's the transfer function? Then we zero that out. Okay. We ignore it. So that means this transform process of transforming the differential equation to the transform domain is actually going to be a little bit easier. Okay. Please understand, we ignore the initial conditions not because they're unimportant in life. They are important in life. Okay, you've ever heard the expression, oh man, did you wake up on the wrong side of the bed today? That affects you for the rest of the day, right? Your initial state, your initial condition does affect you. It's important in life. But in the discussion of transfer function, that doesn't matter. Okay. Transfer functions, we ignore initial conditions. Okay, let's go back and finish this problem. I'm going to rewrite the problem again. Y triple dot plus 4y double dot plus 3y dot plus 2y is equal to 6u dot plus 5u. We're going to transform it now. Y becomes capital Y of S scaled by 2. Y dot becomes S times Y of S scaled by 3. That messy business about the initial conditions we ignore because we're interested in input-output relationships. What do you think would happen here? How would this transform? Any suggestions? I take Y of S. I multiply by S squared. Excellent. And then I put the 4 out here. And then this becomes Y of S cubed. Okay. And over here on the other side, I'm just go ahead and write it, 6 scaling S U of S plus 5 times U of S. Okay. Take the time domain expression in the first line, transform it into transform domain, go from English to French. Instead of having calculus operations, now we have algebra operations, algebra multiplying by S. Now, from here on out, everything is algebra. Okay, so we do algebra operations. And what we're going to do is do algebra operations to find output over input. And so the output over input is Y of S over U of S. It's a ratio. Something over something else. Okay? So let's study this for a moment and think about what algebra we can do. Study this side for a moment and think about what algebra we can do. I need basically to isolate everything so that all the y's over here and all the u's over here. So think about all your algebra tricks that you know to do that. Okay, and there's more than one way to do algebra. But hopefully, no matter what path we take through our algebra, we discover that the end result is 6s plus 5 over s cubed plus 4s squared plus 3s plus 2. And so this is my transfer function model. Okay, the abstract idea is that its input is u, its output is y in the S domain. Okay. Now there are computer tools these days that allow you to use these graphical objects. We'll pull out a little box, put it on our graphical user interface, our tool, and they expect you to fill in the parameters of that model using expressions that look like this. And nobody in the world knows what's going on except us electrical engineers. Okay. It's an abstract idea, but basically it's a representation of that differential equation up there. Okay, so think about it that way. You just transform a differential equation to another language where the work is going to be all done in algebra. Notice what is in a transfer function. What is this? Or this? How would you describe what this is? 2, 3, 4, 5, and 6. Constants. Okay. You see constants. These are the S operators. Okay. In the transform domain, in France, we speak French, so we see the transform operators. So the transfer function is composed of constants multiplying these operators. Notice what you don't see here. We don't see any signal names. There's no I over here. There's no Y over here. There's no X or Z or some signal name. Okay. It's just all constants and operators. So all constants and operators. Constants. The operator S. Okay. No signals. That means there's no U, there's no Y, there's no capital U, there's no capital Y. If we do our algebra to get from this step to this step, and somehow at the end result we see some signal names floating around in there, our conclusion is if in our box we see some signal names, our conclusion is we made some mistake. Okay? And we just need to back up a little bit. Let me try to summarize. Today we talked about transfer function. It is the model that goes into something like this. This is the output. This is the input. Okay. So the transfer function is output over input. It is an expression, it's a ratio in transform domain. Okay. This is the key thing that we want to walk away with today. And what is transform domain? It's this idea that if we take a signal, let's call it Z of t, we can go to another country and say, we're still talking about bread. This is bread in English, this is bread in French. English, T, French, S. I think Laplace is a French word, French name. But if this happens, then Z dot becomes S times Z of S. And the other thing we want to take away from it is that there was this idea of, well, we got to subtract off the initial value of Z, but we kind of ignore this in the transfer function work because we're interested in the input-output relationship. And then if I had written integral of Z dt, that will transform to Z of S over S. So this morning in a nutshell is right there. Any questions, discussions for the benefit of the class? Concerns? Okay, so a reminder, please visit the Canvas page regularly to see old materials, old exams. Try to get to know me by looking at those old exams and figure out what sort of habits the old man has. Okay? One of the things that you'll probably see is that exam 1, problem 1, for many years, exam 1, problem 1 has been a circuits problem. Okay? Because I think electrical engineers, of all people in the world, should be the ones who understand circuits.
No.
Young man back there says no. And he's actually not alone in the world. If you were an undergraduate student at Georgia Tech, your introduction to EE is not circuit analysis. Okay, Georgia Tech, a number of years ago, says that we live in a digital world. It's all about the cell phone and everything like that, working with information. So their introduction to EE is signal processing, digital signal processing. They promoted this idea of DSP first. So circuit analysis is something you take later on. So it is a growing world that our field is growing. So there's more than one way to enter into electrical engineering, but I'm kind of old school, old-fashioned worker, so I think we should understand circuits. So brush off your 2110 circuit analysis and don't trip up on that first problem. You have to analyze some circuits. Matt has graciously recorded materials, and he's already sent me some materials, and they're YouTube videos, and I put links to them in the Canvas page. So you go to the home of the Canvas page, again you see the chart that shows class 1, the topic, homework, so on and so forth, references. Over here there's class number, 1, 2, 3, 4. And so if you click on the number, there should be links. Anything else? All right, let's have a good day.